In this video, I'll introduce chi-square tests. Chi-square tests are useful when conducting inference on categorical variables. There are different types of chi-square tests depending on the number of categorical variables, but let's first introduce the chi-square goodness of fit test. The chi-square goodness of fit test is used to determine if a sample is representative of the population or some specified distribution for a single categorical variable. To understand this test, let's look at an example. Take a standard bag of Skittles. There are approximately 60 individual Skittles in a bag with 5 different color options: red, orange, yellow, green, and purple. You might wonder, in a bag of Skittles, are the colors distributed evenly? If so, we'd expect approximately 12 Skittles of each color in a bag of 60. Say we buy a bag from the store and observe the counts of each color. The notion of chi-square tests is to compare observed counts from a sample with expected counts from a population or specified distribution. In general, the hypotheses can be formalized with the null being that the colors of Skittles are distributed evenly, i.e. the proportion of each color is 1/5. The alternative would be that the colors of Skittles are not distributed evenly, so that at least one proportion is not 1/5. The main assumptions of chi-square tests are that the observations are independent and the expected counts are sufficiently large, usually at least 5. The chi-square distribution is characterized by its degrees of freedom. In the plot, we can see that the distribution is right skewed, but as you increase the degrees of freedom, it approximates a normal distribution. The test statistic is given by this formula, which compares the observed counts O and expected counts E. Intuitively, if there is a large discrepancy between observed and expected counts, this test statistic will be significant. We can add up the contributions of each color to the chi-square test statistic, and using this formula, compute the test statistic to be 2.167. Under the null hypothesis, this test statistic follows a chi-square distribution with c-1 degrees of freedom, where c is the number of levels of the categorical variable. Here, c is 5, so the degrees of freedom are 4, and we can use a chi-square distribution with 4 degrees of freedom to compute a p-value of 0.7486. Thus, we failed to reject the null hypothesis, and we do not have sufficient evidence to conclude that the colors of the Skittles are not distributed evenly. What if we wanted to compare 2 categorical variables? In another video, we talked about A/B testing to compare click-through rates of a website. Well, what if we wanted to compare the engagement of different sections of a news website, say sports, politics, and entertainment? We can display the information comparing 2 categorical variables in a contingency table. The test is very similar to before, with a couple changes. First is the degrees of freedom for the test. It's now r-1 times c-1, where r is the number of levels of the row variable. Here it's 3, and c is the number of levels of the column variable. Here it's 2. Also, to compute the expected counts, we multiply the row and column total and divide by the grand total. For example, for the cell of people who did not click on the sports page, the expected count would be the row total of 300 times the column total of 370 divided by the grand total of 1,000, giving an expected count of 111. This seems quite different than the observed count of 180. We could then set up formal hypotheses to test whether the section and website engagement are dependent or associated. We won't go through all the steps again, but once you have the expected counts, you can compute a test statistic like before, comparing the observed and expected counts. One interesting thing to note is that the test is actually equivalent to the 2 proportion z test when r and c are both equal to 2.